bom, não tá full, mas tá bom.
Okay.
Okay, so welcome everyone to this edition of the Brazilian Algebraic Geometry Seminar. And today it's a great pleasure to introduce my colleague, Oliver Lorscheid from IMPA, who is going to talk about the moduli space of matroids. Go ahead, Oliver.
Okay, thank you very much for this invitation. It's a pleasure to speak here, and yeah, kind of sad that I couldn't follow this seminar during the year because it's my childcare time, but today we swapped duties, so yeah, I'm happy that I at least can contribute. As Carolina said, I will talk about the moduli space of matroids, which is based on a joint work with Matt Baker. Actually, this is from 2 years ago, but incidentally, we got the first referee report last Friday, so it's a good occasion, and this might be published soon. Okay, so before I explain you the outline of this talk, maybe I tell you some words how we got across this project, how we start to work this out. So the story is that Matt Baker had generalized matrix theory to matrix theory over objects, yeah, kind of exotic algebraic objects, which kind of streamlined a lot of the foundational work of matrix theory. And there are different viewpoints on matrix, and one viewpoint was basically saying that a matrix is something like a point in a Grassmannian over F1. Lying a little bit here, but it basically said that this could have a reinterpretation F1 geometry, and I talked to Matt about that, and he said this is very interesting, and thought it was maybe not such an interesting observation, but at some point we started working this out, and once we had written out rigorously what this meant, this observation, we started to observe that this has actually implications on matrix theory, or more precisely on the representation theory of matrix. So we could prove certain, or at that point we could reprove certain theorems about matrix with very different methods that come from algebraic geometry or from more algebraic background, where the proofs before had a very combinatorial proof. And actually we have pursued this program, so we have a follow-up paper, and I mean, there's a whole, if you want, program lined up of future works that we want to do, where we really use these methods to prove new results about matrix theory. So it's not just some nice interpretation of some moduli space, but something that's really useful for matrix theorists. And as a warm-up, I want to present you in a prologue the main characters of the whole story. So these are some of these exotic objects that are important for matrix theory, and that will be in particular importance for this talk. So the first object is not exotic at all, and you know all this is a field with two elements, 0 and 1, together with the opposite multiplication, and the addition is given by the multiplication table on the right. So, I hope you all have seen that. So the next object, it's a bit exotic. It's a Krasner hyperfield. It's a so-called hyperfield, but I will not bother you with axiomatics of hyperfields, which is a bit cumbersome, but describe it to you and later capture it with axiomatics that is general enough to embrace all the objects that we want to consider. The underlying set of the Krasner hyperfield is also 0 and 1, like in F2. So multiplication is also the same, but the addition is kind of distorted. So 0 still acts neutral, but 1 plus 1 is now not defined as 0, but it's multivalued. It can have value 0, or it can have value 1. So in fact, 1 plus 1 is a subset of the Krasner hyperfield. It's the whole Krasner hyperfield. So this is the second protagonist and the first exotic object. The second exotic object is also hyperfield, the sign hyperfield, with 3 elements, 0, 1, -1. By the multiplication is the obvious one, as you would multiply them as real numbers. And the addition table is given on the right, which happens to do the following. I mean, 0 acts neutrally, 1 plus 1 is 1, -1 plus -1 is -1, but 1 plus -1 can be any element of the sign hyperfield. And I mean, addition is always commutative in the structures that we take, so -1 plus 1 is the same. This should be interpreted, I mean, or the motivation for this addition is you should think of how to edit real numbers. If you add 2 positive real numbers, the outcome is positive. If you add 2 negative real numbers, the outcome is negative. But if you add a positive real number and a negative real number, the outcome can be anything, positive, negative, or 0. Okay, and the fourth character here is a regular partial field. And this is not a hyperfield, because instead, I mean, the underlying set is 0, 1, -1, with the same multiplication as sign hyperfield. But instead of addition being multi-valued, it's here partially valued, which means that the sum of 2 elements contains at most 1 element, but it's empty. So 1 plus 1 is not defined. And -1 plus -1 is also not defined, while 1 plus -1 is 0. So these are the 4 main examples that you have to keep in mind, and I'll come back later to it and describe them in a different way. But I mean, if you look at the addition tables and had enough time to meditate over it, you will observe certain properties. For example, there's always a unique additive neutral element, in the sense that for each element, there's a unique element A, there's a unique B, such that 0 is a value for A plus B. There might be other values, but in each row and column, you find exactly 1 0. And I mean, they also satisfy some associativity law, which is harder to see and is actually not relevant for us. Okay, let me, before I dive into giving you some proper definitions, let me outline the talk. So what we want to do here overall in this talk is to connect matrices with algebraic geometry. In 2 ways. We want to construct a modular space of matrices, which is an object in algebraic geometry, and we want to apply algebraic geometry to say something about matrices. So there's an interaction between the 2. But there's a kind of digression here. Algebraic geometry in the usual sense is defined over fields or over rings, while matrices are precisely not defined over these objects, but these are combinatorial objects which kind of capture linear algebra when you don't work over a field. So what we need here to make these 2 areas meet is to have a common basis of certain exotic algebraic structures. So we extend both sides to a larger domain of base fields or base structures, and then we can lay the link between these 2. Then finally, if we have developed the whole pictures, we find applications to prove theorems about representations of matrices. So the talk is structured by, first, in part 1, explains these exotic algebraic structures. Part 2, I want to explain matrices from a certain point of view, so that you have at least a feeling you know what a matrix is. I mean, of course, it requires, of course, to really know that, to understand that if you're not familiar already with matrices. In part 3, I want to explain you how to construct the modular space of matrices, or kind of give you also a rough idea of that. And then in the final part, I explain you how this becomes useful in matrix theory. And the guiding example that will accompany us through this whole talk is the following theorem by Bloodlust from 78, which says that a matrix is regular if and only if it's binary and orientable. This theorem, until 2 years ago, had only kind of a difficult combinatorial proof that's based on Tutt's homotopy theorem. So, well, I don't expect you to be an expert in matrix theory, but Tutt's homotopy theorem is kind of a red herring, which is omnipresent in a lot of theorems around representations of matrices, but which until today doesn't have any lucification. It's a combinatorial proof of, 20 pages, a case-by-case consideration, which is very elementary, but totally not enlightening. And, well, some proofs of this vein got simpler proofs, but I picked this example because we were the first ones who kind of gave a proof that is more conceptual. So if you want to review the structure of the talk, I could tell you that at the end of part 2, we are able to understand this theorem, these terms, matrix, regular, binary, orientable. I will define this for you. And at the end of part 4, we will be able to understand the proof using our methods. Okay, let's dive into part 1, which is about the exotic algebraic objects. Oh, this should be idylls. This is still, well, wipe out the passages, it's an idyll. So an idyll, it's some generalization of a field. A field, all know what this is, and an idyll could be a landscape, a pasture, as mentioned before, or a field. So it's something more general. So the proper definition is that it's a pair F of an abelian group F star, which we should think of the unit group of the idyll. So it's written multiplicatively. And NF, which is the so-called null set, and it's a subset of the group semaring of F star. So it's N adjoint F star, which are finite formal linear combinations of units of elements in F star, where coefficients are non-negative integers, such that a certain list of axioms is satisfied. So the first one is zeros in the null set. So yeah, null is German word for zero, so this makes sense. Then it's additively closed. So whenever we have elements A and B in the null set, then A plus B is in the null set. It's closed under multiplication by units. So whenever A is in the null set and B is a unit, then A times B is in the null set. And then the fourth element, the fourth axiom says that every unit A has a unique additive inverse in the sense that there's a unique unit B, such that A plus B is in the null set. We call B the Greek inverse of A. Just maybe to streamline the axioms more, this first three axioms, 1 to 3, just express that NF is an ideal in the semaring, this group semaring. If you know what's an ideal from semaring. Okay, so some conventions. We denote as the underlying set of attracts a set of all units and zero, which we realize as a subset of the group semaring. So the units are just 1 times the unit, and 0 is the empty sum, the empty formal sum. And we denote the weak inverse of 1 by epsilon. You should think of epsilon as -1, but it's not the -1 in this group semaring. This group semaring doesn't have additive inverses. So that's why I stress this and put an epsilon here. But still, the axiom says that epsilon behaves very much like -1 in the sense that epsilon squared is 1, and that B in F is the weak inverse of A in F if and only if B is equal to epsilon A, so equal to -A, if you think of it as -1. Okay, so let me give you some examples. So in a sense, I'm reviewing the examples from the first slide here. But the first example is a bit more general. If we have a field K, then we can realize this field as an idyll by just taking the unit group of the field, K star. And the null set consists of all finite formal sums of coefficients NA times A, such that this formal sum evaluated as elements in K is actually 0. So these are all finite sums. These are all sums of elements of K that sum to 0. I forgot to say that. Maybe I go one slide up again. This null set should be thought of the elements that sum to 0. So like in this example. And normally what we would do if we work in the realm of rings is to divide by this ideal. So all the elements that should be 0 are actually 0. The problem why we can't do that is because in the realm of semi-rings, quotients don't correspond to ideals. So if you divide out an ideal, there's something like a categorical quotient, but it identifies more than just the ideal to 0 in general. So it can happen that you divide by a proper ideal and the quotient is just this 0 semi-ring. And this will happen in these exotic examples from the first slide. For fields, it's harmless, but still, that's the version as an ideal. And for F2, the unit group is 1, and the null set are all multiples of 1, such that this multiple is 0 in F2. So it's just all even multiples of 1. Okay, the second example of the Krasner hyperfield. It's a idyll that has the same unit group, just 1. And the null set are all multiples of 1 such that 0 is inside. And these are all multiples n times 1, where n is not equal 1. So 0 times 1 is clearly 0. But as from 2 on, you remember 1 plus 1 was both 0 and 1. So 1 plus 1 contains 0. We take 1 plus 1 plus 1, it also contains 0 and 1 because 1 plus 1 already contains both elements. So I mean, this is not a proof, but a heuristic argument why this idyll corresponds to the Krasner hyperfield that we defined intuitively before. So for the rest of this talk, the Krasner hyperfield will be this incarnation as an idyll. Okay, the sign hyperfield can be realized as follows. The units are 1 and epsilon, so all non-zero elements. Epsilon here is the same as -1 from the first slide. But as I explained, it's better to call it epsilon to avoid confusion. And the null set consists of all linear combinations n1 times 1 plus n epsilon times epsilon, such that either n1 and n epsilon are 0, so it's a 0 element, or both elements are non-zero, and then, I mean, this linear combination corresponds to the whole sign hyperfield, because again, when we add 1 and epsilon, we get all elements, and then adding any element to that just stays the whole set. That's, once we are at the whole set and adding things, it stays there. Okay, the last protagonist is the regular partial field, whose unit group is the same, but here the null set are all linear combinations n11 plus n epsilon epsilon, where n1 equals n epsilon, because if they're not equal, then the outcome will be the empty set, which doesn't contain 0. Okay, so by the way, if you have questions, please jeopardize me. It's yeah. Yes, I have the chat open. You can even put it in the chat or just use your microphone. As the last part, to give it a rigorous categorical framework, I introduce morphisms. So morphism of idylls, it's just a structure preserving map. It's nothing funny happening here. So it's a map between the underlying sets that preserves 0 and 1, that preserves multiplication, that preserves this null set in the sense that a linear combination of units A is sent to the same linear combinations of the images of the unit. So in a sense, we can extend F linearly to the group semma ring, and then it maps the null set to the null set. Here are some examples of morphisms. The first is a sign morphism, which maps R to S. And this is a morphism just because the sign hyperfield was defined in the way as we added real numbers, taking care that the sum of a positive and a negative real number could be everything. Okay, this is just for, because it's a nice example. The example, what's really relevant for this talk is that there's a terminal object and an initial object. So the Krasner hyperfield is a terminal object, which means that for every idyll F, there's a unique morphism from F to the Krasner hyperfield that sends units A to 1 and 0 to 0. And well, I leave this as an exercise for you to verify it. It's just an immediate check. And the initial object is the regular partial field, F1 plus minus. And this maps 0 to 0, 1 to 1, and epsilon to epsilon. So the regular partial field has the minimal addition that's required by the axiomatization of an idyll. Okay, part 2. Now I want to tell you in a nutshell what matroids are. For the rest of the talk, we fix two numbers, R and N. R is between 0 and N. Two integers, sorry. And let E be the set from 1 to N. And K denotes a field. So I do kind of an unusual approach here. I first will define you what a K matrix is, which is something that was not defined before. Well, I'm lying here a little bit. I think Dress and Wenzel already had a definition for that, but this was something that was not commonly considered by matrix theorists. Let me say that. But since we know what linear algebra over a field is, it's very easy for me to tell you what a matrix over a field is. And then you can graph the analogon over other exotic structures. So a K-matrix of rank R is nothing else than an R-dimensional subspace L of K to the N. And well, we say of rank R on the ground set E, so we should better identify K to the N with maps from E to K, where E is our ground set. But it's the same thing. Okay, so it's nothing else. We have a vector space with fixed spaces, and we take an R-dimensional subspace. Here's a cryptomorphic description. And well, if you don't know matrix theory, you might not have heard the word cryptomorphism. This basically means it's an equivalent description, but not obviously equivalent. So matrix theorists call this a cryptomorphism for some reason. It doesn't have any proper mathematical meaning. So K-matrix, well, it's the same thing as a point in the Grassmannian Rn, a K-rational point. And we can realize the Grassmannian as a subset in the projective space of some dimension capital N, which is N choose R minus 1. And inside the projective space, a set homogeneous coordinates delta I, where I ranks over the R subsets of E. So I don't denote this by E choose R. And with that, we already have a geometric interpretation of matrix over a field. It's a point in the Grassmannian. And I mean, here we are already basically at this observation that I talked about in the beginning. So a matrix is a point in the Grassmannian if we work over a field. Well, matrices themselves are defined with coefficients in some other object. And this will not suffice to describe them. So we would like to extend this geometric picture to other realms. Well, the first thing is that we have to give up this geometric picture. I mean, this comes back later with F1 geometry, but I don't want to assume that yet. So how do you explain to a first-year student who knows linear algebra, but haven't seen what's algebraic geometry or Grassmannian? How do you explain what's the point in a Grassmannian to him? Well, there's an easy way. You can say a K matrix, so point in a Grassmannian, it's a K star class of what we call Grassmann-Plücker function, so of a non-zero map delta from E choose R to K. So delta takes every R subset I of E to its Plücker coordinate, delta I. And this function should satisfy the Plücker relations. Okay, we'll not read out the Plücker relations. I hope this is something you've all seen. But this is a definition where you don't need any algebraic geometry for it. You just need to know what's a function, basically. And then with this definition, we can... Okay, I don't know how this was for you. Did you see what happened? That was kind of a blip. I go back. Okay, this is... if you have kids, this is what you do on the weekend with your kids. You have these two pictures and you have to identify the mistakes or the difference between the pictures. So here it comes again. Did you find the 10 differences? Okay, we'll mark them in green for you. So we can extend this definition now to adults because it doesn't involve any advanced theory. So if F is an adult, replace the field K by an adult, then F matrix is an F star class. By the way, F star means just we're multiplying the function with values of F star, which is an obvious operation here. We replace this by functions from E choose R to F, which are not constant zero, that satisfy the Plücker relations, which are just, it's the same combinatorial recipe, but here we're taking care that we replace -1 by epsilon, and we replace the equality equal to 0 by element of the node set. So I mean, we do kind of the most straightforward, obvious generalization group passages. And that's what an F matrix is over an idyll. So now you have in your hands more or less the most general definition of matrix that there is on the market at the moment. I'm kind of cheating a little bit here, but I mean, it's a certain point of view. So the real task is here to really understand what's happening with these objects. I mean, this is kind of a function that does something similar as the Plücker coordinates in the Grassmannian, what's happening here. But to give you something concrete in the hands, I will define you know what is a matroid. A matroid is nothing else than a K matrix. So matrix with coefficients in the idyll, which is across an hyperfield. Here's some examples. So the first one's not relevant for the talk, but I got very quickly over it just for educational reasons because it's a large source of matrix. If we have a connected graph gamma with edge set E, which will be the underlying set of the graph, and R is the difference of the number of edges minus the first Betti number of the graph. So it's equal to the number of edges of the spanning graph of the graph, spanning trees of the graph. Then the Grassmann-Plücker function for this graph is given by sending an R subset I of E to 1 if I is a spanning tree of gamma and to 0 if not. So if you're a little bit used to matrix, the spanning trees will give the basis of the matrix. Okay, and this is a Grassmann-Plücker function, which I give as an exercise. It's, yeah, I mean, this is not hard, all this basic matrix theoretic stuff, but I don't want to go through the combinatorial proofs here. And this defines a matrix M. The matrix associated with the graph. Another source of matrix come actually from linear algebra, and this is a construction that we will use later. That's important for this talk. So if F is a field K, and we consider an R-dimensional subspace L of K to the n, this Grassmann-Plucker function delta from e choose r to k, then we can consider the push forward of this Grassmann-Plucker function along the terminal map. So tk was this map, this unique map from k to the Krasner hyperfield, which sends all units to 1. And if we compose the Grassmann-Plucker function delta with tk, then this again is a Grassmann-Plucker function, but with values in k. And this defines a matroid. And this is the so-called underlying matroid of the given k matrix, this r-dimensional subspace. And conversely, we say that a matroid M is representable over a field if it comes from a subspace in this way. And this representability is really the representability that I talked about in the beginning, when I said we care for representations here of matroids. So let me generalize this definition a little bit to all idylls. So if F is an idyll and TF is a terminal map to the Krasner hyperfield, then a matroid M, so K matroid M, is representable over F if there's a Grassmann-Plucker function with values in F, such that M is represented by the composition TF after delta. So it's the underlying matroid of this Grassmann-Plucker function over F. And now we care about these questions: when is a matroid representable over another idyll? So this will, at least in the final part, will be the game of the talk. So here's some more terminology. A matroid is called regular if M is representable over the regular partial field, F1 plus minus. Matroid is binary if it's representable over the finite field with 2 elements. A matroid is orientable if it's representable over the sign hyperfield S. So now you have seen all our 4 protagonists in action, and you're able to understand the theorem of Bloodlust and Werner's from the beginning. So matrix regular if and only if it's binary and orientable. In other words, the matroid is representable over the regular partial field if and only if it's representable over both F2 and S. Okay, so end of part 2. Good point for questions before we change the flavor of the talk a little bit. Okay. So next part, I want to explain you how to construct the moduli spaces, but well, I just give you a taste of it because it requires setting up kind of F1 geometry, and I mean, this is something I cannot do now in 10 minutes. But I will do this a little bit hand-wavingly just to give you an impression of how this is working. And the core objects that's used here are ordered blueprints. So I'll give you a proper definition of that, and then I will not define these things properly anymore. An ordered blueprint, it's yeah, something not so hard. It's a triple of B dot, B plus, and less or equal, where B plus is a semi-ring, and semi-ring for me in this talk means always it's commutative with 0 and 1. So like rings in algebraic geometry are also the nicest possible rings among all variations how you could define a ring. B dot is a multiplicative closed subset of B plus that contains 0 and 1, and that generates B plus as a semi-ring. So it's a submonoid if you want, that contains 0 and generates it. And less or equal is a partial order on B plus that's additive and multiplicative in the sense that x less or equal to y implies that x plus z is less or equal to y plus z, and x times z is less or equal to y times z. Okay, here's the main example. An ordered blueprint is a generalization of an idyll, so we can realize idylls as ordered blueprints. So if we have an idyll F with unit group F star and node set NF, then this can be realized as ordered blueprint B, whose ambient semiring B plus is just this group semiring that appeared before, and it joins F star, whose underlying monoid is just the underlying set of the ideal F, which is the unit group together with 0 realized as a subset of the semiring. And this turns out to be really multiplicatively closed and to generate B plus, because it's generated by F star. And the null set is encoded in the partial order, which just looks a little bit funny at the beginning, but I mean, that's the way that it works. So the partial order is the smallest additive multiplicative partial order on the semiring, for which 0 is less or equal to a finite formal sum over NA times A, whenever sum of NA times A is in the null set. So we take the smallest partial order that's additive multiplicative, such that the null set is something like a positive cone, if you want to look at, say that elements larger than 0 are positive. Okay, and I mean, this kind of gives a nice realization. There's a categorical concept, so it's in which it becomes full subcategory, but this is already going further than what I want to tell you in detail. Now I just outline what we're doing. So ordered, I didn't say why we consider ordered blueprints. The reason is that ideals it's a generalization of fields, right? It's kind of, and it's a generalization of fields because every non-zero element is invertible in mathematical sense. But if you want to talk about algebraic geometry, we need, in the classical sense, we need something like rings where you also have elements that are not invertible, where you have ideals and so on, prime ideals in particular. And ordered blueprints are doing this for us. And I mean, it's kind of a more general theory, this ordered blueprints, but I developed algebraic geometry for ordered blueprints already before for different purpose, for tropical geometry. So this was just lying around and fitted the purpose. That's why I ordered blueprints. So to define ordered blue schemes, we just go, we take Hartshorne chapter 2 and we take all the constructions and interpret them for ordered blueprints. Oh, well, there are some things that are a little subtle, but basically it's the same recipe. So we can define first of all the notion of ideals and prime ideals. We can say what the localization is. And with this, we can define spec B as a set of prime ideals whose topology is defined in terms of localization at one element. And the structure sheaf is also defined in terms of localizations on this principal opens. And there's also a variant, proj B, for graded ordered blueprints, which works like in usual projective geometry. And then gluing kind of local pieces together, we arrive at the notion of ordered blue schemes, which are topological spaces with structure sheaf in the category of ordered blueprints. And then there's one more bit that we need, which are line bundles. So a line bundle is something that is locally isomorphic to the structure sheaf, which is also no problem here because we have topological space and we take a sheaf in ordered blueprints, which is locally isomorphic to the restriction of the structure sheaf to the open. These are all more or less straightforward definitions, and I appeal to you to just take your intuition from usual algebraic geometry, which works fine, totally fine for the purpose of this talk. So I'm aiming at defining modular space. So to really have a modular space, we need something like a modular problem. And we want to recover something like a universal family. So matrices are only defined over spectra of ideals, so over fields. But to formulate a modular problem, we have to say, a modular problem is a functor from all of our geometric objects to sets. And then we want to find a modular space which represents this functor. So here's an extension of matrices, which are defined over ideals, to matrix bundles, which are now defined over ordered blue schemes. And I mean, here you might already see that in the background there's something happening like embeddings into projective space. So we have to talk about ample line bundles. Well, so ample goes under the rug. But so first of all, we define what's a Grassmann-Plücker function on ordered blue scheme X. And this is a line bundle L on X together with a map from E choose R into the global sections of the line bundle that satisfies the Plücker relations and for which the family of sections delta I generates L. So delta I are the images of the R subsets of E under this Grassmann-Plücker function delta. I don't write out the Plücker relations, it's an obvious recipe. Just want to remark, why does the family of global section has to generate L? Well, this is the right generalization of the condition that the Grassmann-Plücker function is not zero. And as I said before, we want to talk about embeddings into projective space, so this is a condition that you're used from in usual projective geometry. A matrix bundle is it's just a class of a Grassmann-Plücker function. So it's an isomorphism class, which means that it's induced by an isomorphism of line bundles, which induces an isomorphism between the global sections and therefore connects two different Grassmann-Plücker functions. And here's just a remark that this really extends the notion of an F matrix. If you have an ideal F, then, well, a matrix bundle on spec F is the same as an F matrix. Basically, because spec F is a point, the only prime ideal is zero ideal, and the global sections of spec F in any line bundle, which must be trivial, is F itself. So the global sections here, gamma X into L, is just F. So it's the same Grassmann-Plücker function, and then everything, all the conditions upstairs of a matrix bundle translate into the condition of an F matrix. So this means that we really have an extension of F matrix to matrix bundles. The matrix space is defined as something with the following formula, which I put in hyphens because I can't explain this properly to you. It's a proj of F1 plus minus, which is a regular partial field, associate variables Ti, where I varies over all R subsets of E, modulo the Plücker relations. This, I mean, whatever this means, this is a graded ordered blueprint to which we can apply the proj construction. And this stands in complete analogy to the definition of the usual Grassmannian as a proj of some homogeneous algebra or field. And the analogy goes further in the sense that the matrix space, mod RE, embeds into an ambient projective space, which contains all the Plücker coordinates. And this allows us to define the universal bundle L-unif as a pullback of O1 from Pn, so it's just a twisted line bundle. Once again, appeal to your intuition from usual projective geometry. And we define the universal Grassmann-Plücker function as a Grassmann-Plücker function in the global sections of this universal line bundle that sends I to Ti, which is a global section, just like in usual algebraic geometry. And with that, we have here our central theorem of the paper, which is that the matrix space, mod RE, is a fine modular space of matrix bundles. So this means that the functor sending an ordered blue scheme X to the set of its matrix bundles is represented by this ordered blue schemes. So it's equal to the morphisms from X into this ordered blue scheme. And the universal matrix, the universal family here is a matrix bundle which is defined by the universal Grassmann-Plücker function. So any other matrix bundle is given by a pullback via uniquely defined morphism into the matrix space. In particular, this is true for an idyll. So this F is an idyll, then taking the F rational points of the matrix space, which are morphisms chi from spec F into the matrix space, the definition, corresponds bijectively to the F matrix of rank R on E by just taking the pullback of the universal Grassmann-Plücker function. So if you want, this is another cryptomorphism of matrix. So matrix over an idyll F is nothing else than an F rational point of the matrix space, which now kind of explains this observation with which the whole project started. Okay, so this is end of part 3. Again, a good place for questions if you have any. Eduardo thinking. It's good that I can see your videos. It's the first time. For Zoom, it's not possible.
Trying to observe.
Okay. But then to how do you say, to cover the void of more talking, let me say it's this corollary. Keep it in mind, because for the fourth part we will start by turning around the corollary. So, Eduardo, you want?
No.
Okay, then let me go on to part 4, foundations of matrix. I'll explain you what this is and how to apply it.
Tem uma pergunta no chat.
Okay. I have a question. Where does the name matrix come from? Okay, it's some derivation from matrix, because what I explained before, that a matrix can be represented by subspace L of K to the R, and can also, the subspace can be represented by a matrix which consists of the base vectors of L. And then you will derive a matrix from a matrix. I think it's coming from there. But the notions in matrix theory sound very much like in linear algebra, but they're used in a little twisted ways. This is very confusing. So matrix doesn't correspond to a matrix in any sense, but it can be, matrix can be derived from it. Okay, here we, as I said, we turn around the last corollary in the case of the Krasner hyperfield. So matrix of rank R on E correspond bijectively to k rational points of the matrix space. And this associates with the matrix a morphism from spec K to matrix space. This morphism goes from the point, spec of K, into the matrix space. So the image is also just one point. We denote the image point by xn. The image point has a residue field. And we call this residue field the universal idyll. And denote by kn. And it's indeed an idyll, the residue field. Like usually the residue fields at a point of scheme is a field. So idylls are really the kind of objects that are replacing fields in our more ambient theory. And this universal idyll knows a lot about the matrix M. So the first application are realization spaces. So realization space is something that was already investigated before. So if you have a matrix M and a field K with determinant Tk into the Krasner hyperfield, then the realization space of M over K is this script Mk, which is a subspace of the Grassmannian. It's a locally closed subvariety, but a subset, which consists of all Plücker coordinates whose underlying matrix is M. And there's this famous universality theorem due to Miev and with variation by Fork and Vakil, which says that this realization space can be arbitrarily complicated. Well, arbitrarily complicated means for fixed K, but with M varying. So we take more and more complicated matrix. This can be an arbitrarily complicated variety. For example, the version of what Kiel shows that every type of singularity occurs in this type of variety. And in a sense, every variety over K is equivalent to this realization space, but I don't want to tell you what this equivalence is. It's because an isomorphism. Something has a projection from a representation space to each scheme, a projection of a certain type. Okay, here's the connection with the residue field, the universal idyll. So if K is the universal idyll of M, then it represents a realization space in the sense that the realization space of M over K corresponds bijectively to the morphisms from Km to K. Which says that this idyll carries basically all the information about representations. So in particular, M is representable over K if and only if there exists at least one morphism from Km to K. So all this is a little bit, I mean, the proof of this theorem is very easy. It just follows immediately from the modular property and the fact that a field has just one point. So the image is a point and the morphism to the modular space must factor through a morphism to spec of the universal idyll. But the striking thing here with the corollary is that we can rephrase questions about representability of a matroid in terms of the existence of a morphism from the universal idyll to K. So we are boiling this down to an algebraic problem, if you allow me to call these exotic objects idylls algebraic objects. Well, the down part here is that, I mean, it's this very theorem, the universality theorem, this realization space can be arbitrarily complicated. So this universal idylls also must be arbitrarily complicated. And this might not be very useful for explicit statements because it's just getting too complicated. By the way, it would be interesting to pin down what it means for the universal idyll to be arbitrarily complicated. I don't know, I mean, it's not just totally arbitrary, but the combinatorial becomes complicated for sure. So what we do is using the following observation. For many idylls F, it's true that a function, a non-zero map, delta from the R subsets of E to the idyll, whose underlying matroid is M, so I mean, given M and a non-zero function delta whose underlying matrix is M, then delta is a Grassmann-Plücker function if and only if it satisfies the three-term Plücker relations. So just to make clear that you understand, I didn't require that delta is a Grassmann-Plücker function here. I just said it's a map and the composition is terminal map represents the matrix. So the composition is a Grassmann-Plücker function over K, but delta itself might not be. But the statement says for many idylls F, it satisfies to check the three terms Plücker relations. So all Plücker relations where we only have three terms in the sum. So this subsets I and J intersect in a subset of cardinality R minus 2. It's like the Plücker relation for the Grassmannian 2-4, which has three terms. But for other Grassmannians, we have Plücker relations with more terms, which we filter out. Okay, for the purpose of this talk, we call idylls with the property perfect idyll. So it's the perfect landscapes, perfect field, just the nice things you can imagine. Well, there's another definition, a proper definition of what's the perfect idyll in the literature, but which implies this property, and it's not clear if it's equivalent or not. But for simplicity, let me call this perfect idyll here. And there are many examples of perfect idylls. For example, all fields are perfect idylls. Krasner hyperfield, sine hyperfield, and F1 plus minus are perfect idylls. So all the examples that we care for in this talk are perfect idylls, and which means that it satisfies to check the three terms Plücker relations. So just to check, we start a little late. Do you have something like 5 minutes to conclude?
Sure, go ahead.
Yeah, okay, thank you. So what we do now, when we're interested in representation theory over perfect ideals, is to twist this definition of the universal ideal, and we define the universal pasture. Here comes back this pasture, which was erroneously still on one of the early slides. And this is the same thing as the universal ideal, but we don't divide out by all Plücker relations, but only by the three-term Plücker relations. We just forget about all the other Plücker relations. So in a sense, we boil down the combinatorials to something that's easier to handle, and which is enough to talk about representability about over ideals that we care about. As the universal pasture is still kind of a large object, so we find something which is even better to handle, which is a foundation. So which is defined as a sub-ideal, which is defined by the cross ratios, which are expressions something like T13 times T24 over T14 times T23, if we're in a Grassmannian 2-4. Just a classical cross ratio in the generalization to all Grassmannians, just by taking kind of interchanging two indices, taking 4 indices and taking 2 kind of combinations into 2 sets. Okay, so there's a proposition of Wenzel, which implies the following. Namely that Fm is something like the constant field of the universal pasture, or more concretely, it's the smallest sub-ideal such that the quotient of the respective units groups is a free abelian group, and the null set of the universal pasture is, in a sense, generated by the null set of the universal ideal, by the sense that we just take an element of the null set of the foundation. We take an element of the null set of the foundation, and then we multiply it by unit of the universal pasture, and we get all other elements of the null set of the universal pasture. Okay, by the way, this proposition, this is a crucial part where the homotopy theorem of Tat is hidden. This kind of awful combinatorial, where the statement is maybe not so complicated. It's complicated, the statement, but not as complicated as the proof. But it goes into here in a very clean form, saying that something generated by the cross ratios is something like a constant field, and Pm is something like a rational function field over Fm. Okay, here's the last slide. So I repeat. I know it's the last slide, it's true, but first of all, there's a theorem which is the analog of the corollary before. So the foundation, it represents a certain functor, I mean tautologically, but a meaningful functor, namely taking the scaling classes of matrices. But this implies in particular that if M is a matrix with foundation Fm and F is perfect ideal, then M is representable over F if and only if there's a morphism from the foundation Fm to F. So we're replacing in the statement the universal ideal, which is a complicated object, by the foundation, which is very approachable to calculations. One thing that we can prove, and this is a proof that's not very hard, this follows, I mean, each proof is kind of a page or so. It's without doing combinatorics, it's a very conceptual proof, just manipulating algebraic structures. So matroid is regular if and only if the foundation is a regular partial field, which kind of is a nice statement because it links directly to the regular partial field. And it's matroid, a matrix binary if and only if the foundation is either the regular partial field or the field with 2 elements, which is also very easy characterization. Here's again, last but not least, the theorem of Bloodlust. A matrix is regular if and only if it's binary and orientable. And now we're able to prove it. So let's assume M is binary and orientable. Then this means, by the theorem above, that the foundation is either F1 plus minus or F2, this is characterization of binary matrix, and M is orientable. Now, this is equivalent to the foundation of Fm being F1 plus minus, because there's no morphism from F2 to the sign hyperfield. This is using the first theorem on the slides. Since there's no morphism from F2 to S, this M here, which is binary orientable, cannot be representable over the sign hyperfield. Sorry, I mixed this up. M is orientable, so there has to be a morphism from Fm to S, but there's no morphism from F2 to S, so we exclude F2 as a foundation. Then use the middle theorem again and conclude that M is regular. And this is a proof of this theorem with our methods. And this is the point where I stop this talk. Thank you.
Thank you, Oliver. Are there questions or comments?
So, Oliver, what can you say about this moduli space of matroids? Is it regular in some sense? For instance?
I didn't understand. Is it what?
Regular, non-singular, for instance? In some sense?
This is a tricky question, because these things are not yet defined for order blue schemes. So, in a sense, I mean, it's not clear what's a smooth morphism for order blue schemes, and I mean, a regular local ring.
Because as I understand
Yeah,
it's a generalization of the Grassmannian in some sense,
Yeah.
right? And
Yeah,
the Grassmannian is a very rich object, like you can do Schubert calculus, you can do a bunch of things which are very useful. What can you say
Yeah.
about the structure of this space?
I mean, about smoothness, I don't know, because we don't have a concept. I don't know if regularity makes any sense for order blueprints.
Uh-huh.
So this I don't know. But it has a lot of other properties that are in common with the Grassmannian. So you get the usual affine covering. So these are, in a sense,
Affine covering.
Yeah, the Grassmannians are birational varieties. Sorry.
Yeah.
They're birational to some affine space or projective space. Yeah, you have all these combinatorics. I mean, how you deal with coverings of affines. You can talk about Schubert decomposition in the same sense, but don't ask me about Schubert calculus because cohomology is not defined.
Also, usually when we try to think geometrically, we go to an algebraically closed field. Can you do that? I mean,
this is not so clear what's an algebraically closed field in this context. So,
because you have several, I mean, for instance, the theorem that you're showing there, right? I mean, you're talking about the residual field somehow. So depending on the residual field, you have a different property of the matroid. But geometrically, we would go to some larger field. But that's not possible.
Okay, I mean, if you really want to think, ask about the geometry, like the complex geometry of these things or so. Well, there may be two answers. The second one is a trick, but the first one is that, it's not clear what's an algebraic closure or so on. And if you look at the underlying space of the Grassmannian, so the prime ideals, this looks very different than for usual schemes. Namely, you have, let me start with projective space, or it's the same for Grassmannian. You have only one point for each stratum of the Grassmannian, which is defined by the vanishing and non-vanishing of points. So for the projective space, it's a toric variety, which has torus orbits, and for each torus orbit, you have exactly 1 point in the ordered blue version of the projective space. And something similar is happening for the Grassmannian. So the whole big cell of the Grassmannian, where you don't meet any coordinate type of plane. It's just one scheme theoretical point, which looks a little bit odd, maybe at first sight. But The game of the rule here is you're not so much interested in the underlying topological space, but you're more interested in spaces of k-rational points. These are more spaces that say something. And then you recover similar things as before. And especially for a field, it's just the Grassmannian over a field. So you can do this for the complex numbers. And this is a trick I mentioned. You can even do something, you can take the associated scheme. So the associated scheme to the modular space of matroids would be the Grassmannian over the integers. And from that you can pass to your favorite algebraically closed field. So there's kind of a functor to really go to usual geometry, but then you forget everything about this combinatorial aspects that these schemes carry on top. So maybe, sorry, this is a lengthy answer, but maybe this is a better point of viewing that these order blue schemes are something like usual schemes, maybe over an algebraically closed field, together with a descent datum, like descent datum to a smaller field, that's even stronger. It doesn't have only arithmetic information to go to the smaller field, but also combinatorial information, which kind of makes it more rigid and goes to this F1 world. Okay.
Are there more questions or comments?
I would have one more algebraic.
Go ahead, Leterio.
So my question is, I am used to think to the Grassmannian as a suitable subset, then depending on the structure, you can give also some structure of algebraic variety. But let's say, set theoretically, as some subset of exterior powers, and I see exterior powers as degree of the exterior algebra. What is the exterior algebra in your context? I'm just wondering.
Yeah, I have to think if this is possible. I never thought about that question, so give me a sec.
Do you want I repeat the question?
No, I think I got it.
Okay.
I got the question, what's the exterior algebra in this context?
Yes, yes.
So I think this makes sense. You can define tensor products, and if you want to do something like this, the rule of the game is, you have this triple of a monoid, an ambient semi-ring, and a partial order. And if you want to do constructions, algebraically at least, geometry is a different task, algebraically, then you try to do this constructions with each object. So tensor product of semi-rings, it's no problem. It's commutative semi-rings, it's like for commutative rings. The tensor product of monoids, the submonoids, this is just a submonoid of all pure tensors. So you don't take linear combinations, but all pure tensors, which defines your submonoid. And finally, the partial order is just the smallest partial order subset, so canonical inclusions, homomorphisms, something like that. So this is possible to define. And the exterior algebra is a quotient that's defined. You can do this by all relations, basically, but for the exterior algebra, it's very nice because it's just defined by binomial relations. So you just have to say that two elements are equal and you pass through quotient by some congruence. And I think this is perfectly fine to define with ordered blueprints. And
so could it be what John Siracusa calls the tropical Grassmannians? You know that there is this paper of John Siracusa studies tropical, but for instance, the tropical Grassmannian is just the exterior algebra modulo the squares of a basis element. And I think that there is some relations of your work with this, also because then they start speaking about matroids and so on. So I was just wondering, I'm not an expert, of course.
Yeah, this is true. I had a look at that. They do something funny, which only works in the idempotent context. These relations are a bit different than usually. So I thought of that a bit, and I didn't see how this fits into this more general context here, where we take also fields into consideration. But My feeling is that there must be kind of a proper viewpoint on the work of Giancarlo Racusa so that it fits in here, but I don't know how to do that. So if you see how to do that, that would be super interesting.
Okay, thanks.
Are there any more questions or comments for Oliver? I have a quick question, Oliver. It's just a very naive question, but when I think of a Grassmannian, I think of it as a homogeneous space and its automorphism group. I haven't noticed, is there any group action taking place here, or it just doesn't appear at all in this context?
Yeah, this is, okay, the torus, I mean, normally you have GL or PGLN acting on the Grassmannian. For the torus inside PGLN, it just acts as usual. It acts as a group scheme. It just, I mean, if you define the group scheme action, it's a categorical definition. It doesn't talk about schemes or something, but it's some diagrams in a category. And you put up the same diagrams here, and it works perfectly. For PGLN, I mean, for groups that have that are not a torus or not just how do you call this, a unitarizable group? I guess so. Multiplicative group schemes are also harmless. You cannot realize them as group schemes in the F1 context, literally. But there's some yoga that you can do to, I mean, you bend the category of order blue schemes by doing something else, and then you regain all this group action. So there's an answer with some more elaborate setups than what I hinted at today. It's possible to regain the group action, and then it works as in the classical case. It has the same combinatorics. I mean, you have a version of PGLN acting on the Grassmannian here. Mm-hmm. Yes.
Thank you, Oliver. So, is there any more questions for Oliver or comments?
Yeah. Hello, I have
yes,
one.
Go ahead.
But it's more philosophical and maybe more related with the terminology that you are using here. These exotic fields and exotic algebraic structure that you introduced in order to study this. This remembers to me a lot to this search for the field of one element. Is there any connection with that? So you have a candidate in your theory that will behave well when you substitute fields by something that should behave like a field with one element.
Yes, this is actually where the whole business of blueprints and blue schemes started with from F1 geometry. So this doesn't show up here because we need, for this theory to work, something like additive inverse. We need this epsilon. And the field with one element doesn't have inverses. Mm-hmm. But there's a common joke, the field with one element is actually not a field and it has two elements, 0 and 1. So the version as an ordered blueprint would be the monoid 0, 1. The ambient summary are the natural numbers and the partial order is just trivial, equality of elements. This would be the version of F1 within this framework. And then you have F1 geometry also covered by what I outlined in part 3 here.
Mm-hmm. Really interesting.
And this F1 plus minus is very closely connected to F1, which is a field with one element. This plus minus is a functorial construction in the background, which I didn't explain.
Mm-hmm. Yeah, I am guessing if this kind of a structure can be extended to other places where this kind of algebraic structure is needed. It's really interesting. Thank you.
Okay, are there any more questions or comments for Oliver? So if not, then let's thank Oliver again for this very nice talk. Thank you, Oliver.
Yeah, thank you very much. It was a pleasure to be here.
Thanks, Oliver.
Thanks, Oliver.
Bye. Take good care. Mars Brain. That's a good name, Letizia.
Thanks.
Maybe you want to stop sharing your slides, Oliver, so that
yeah,
we can see.
You are still recording.
Ah, yes, that's true. Let me stop. Thank you, Jorge. Okay.